let's continue where we start last time. So I hope I convinced you that the way we should think, or it's also the way we really think about galaxies, it's not through these merger trees that we saw previously, but it's really this kind of cycle, the continuous cycle of baryons, and the evolution of galaxies through the inflows, outflows, ejecta of the material, and reaccretion, and so on and so forth. And this was really a sort of paradigm shift in our way of understanding of how galaxies form and evolve. And now, so the question is there some kind of simplify or simple model that allow us to understand this baryon cycle and how these galaxies evolve through this or grow through this evolving equilibrium? And there are a few models, and one of them is called the equilibrium model. So let's go briefly through that to see whether we can understand some processes and how they impact the galaxy individual processes or properties. Sorry. So on larger scale, we have the incoming gas that is accreted from really large scale. So let's call it the inflow rate, if you can see that. And so this inflow rate, so essentially the mass that is inflowing per some time. So what is that? Is on larger scale is driven simply by the gravity, so that's this m dot grav. But we know that not all the gas that arrives to the boundary of the halo or that is accreted on large scales will make it down to the galaxy. So we will introduce some parameter zeta that will tell you what fraction of that gas makes it down to the galaxy. And then you have another inflowing material, which is this material that was expelled previously, and now it's coming back, so this recycling of the material. So this will be our inflow. Now, in terms of what is leaving the galaxy, so the outflow, so this is related to the star formation rate, so you produce the stars and then you generate these outflows. And the way to parameterize it is this through this eta, so-called mass loading factor, which is essentially just the outflow rate divided by star formation rate. So now we can write this all together. So in the equilibrium, you have on one side the inflow. On the other side, you have what leaves, so that's the outflow, but also the star formation. So you are losing the gas in the galaxy because you convert your gas to the star formation, to stars. And you just simply put the things together, and you can express in this quite simple equilibrium model what is expected star formation rate of these galaxies. And it essentially depends only on three parameters. So this mass loading eta factor, this fraction of gas that makes it to the galaxy, and this recycling. And this is essentially what simulations broadly really tell us that how this is happening. So what about other properties? So we talked about metals. We said that metals are very important. So the metallicity can be written as this yield factor times the star formation rate. So metals are produced in stars. So as stars are formed, star formation is ongoing. You have this fraction of metals that you will produce. And essentially, the metallicity is that you enrich the gas by this metal. So what is the source that you are going to enrich? Is this inflow rate, but not the part of the recycling gas, because this recycled gas is already enriched. Okay? So you end up having the metallicity being expressed as this metal yield divided by 1 plus eta. So, and you see that there is this nice connection between the metals and outflows. And imagine that if you fix this yield value, so like to levels of its some number of, let's say, solar value or something like that, you have a direct relation between the metallicity and the outflow. So there is a way to sort of observationally or even in simulation to try to connect the feedback by observing the metals, how this feedback is able to enrich all the gas. And if we have some relation between the metals and metallicity and, for example, stellar mass of object, then we are able to tell something about outflows. And we will see that this is indeed the case. Okay, so what are the consequences of this? I will show you a few sort of very well established, observed scaling relations. So probably one of the most famous one is called the main sequence. So it's the relation between the star formation rate of galaxies and their stellar mass. So in this log-log space, it's almost linear. And so we see that galaxies that are more massive tend to form more stars. They have higher star formation rate. And this is not terribly surprising, okay? The more massive the galaxy is, deeper the potential well, so it can attract more the gas. It will be transformed into stars. We know that this relation evolves with the redshift, so at the given stellar mass, the star formation rate was higher in a higher redshift universe. Again, nothing terribly surprising. Density was higher. The gas needed less time to, everything was more compact. There was less time needed to convert stars. So it seems like all this star formation, this main sequence for star-forming galaxies seems to be a basic prediction of this galaxy formation model. So now the question is this something like this sensitive to the feedback? So if we ask the question, we want to learn more about the feedback, can we use this main sequence? It turns out that to zeroth order, this is not very much sensitive to this feedback and this outflow. Why? Because imagine some galaxy accretes some gas, and this gas will be transformed into stars, and essentially the stellar mass is to zero order just the integral of the star formation rate over the time. Okay, so you proportionally, so by moving, you will move along the main sequence if you change the amount of gas that you have, but you won't go to that much above and below at zero order. What about the cold gas fractions? Again, in observation. So what I'm showing here, what is shown here is the cold gas fraction defined as either the mass of the gas divided by the stellar mass or divided by stellar mass plus the mass of the gas. It doesn't really matter, as a function of stellar mass. So again, we see that there is some well-known scaling relation that tells you that more massive galaxies tend to have less gas, and at higher redshift, this gas fraction was higher. Again, the question is this sensitive to this feedback? And again, it turns out, maybe quite surprisingly, not that much, because again, you change the amount of gas through the feedback or something like that, but you also change proportionally the stellar mass that is produced through the star formation. So on zeroth order, it's not very sensitive to this feedback. So what about metals? I already said that metals should be a nice tracer of this feedback. So there is this very well-known mass-metallicity relation saying that more massive galaxies tend to have higher higher metallicity. And this relation also evolves with redshift. So at higher redshift, the metallicity was lower, right? There was not enough time still to enrich all the gas, and all the galaxies didn't have that much of the metals. And you can see that, for example, here this mass. So the mass metallicity relation is one of the tightest relations in the extragalactic astrophysics. I think that the scatter is officially something like 0.1 dex, which means that if you know the mass of your galaxy, you know its metallicity to a precision of like 0.1 dex, which is pretty amazing. And if we go back to this relation I was showing before, that metallicity scales like 1 over, let's say, mass loading factor related to the outflows, you can directly sort of constrain in some mass regimes. If you know the slope of this relation, you can constrain nicely with metallicities these outflows. So now all these relations have some interesting property, which is that they're scatters. Obviously, there is some scatter, but this scatter is very often correlated with other physical processes. So in case of mass metallicity relation, there is this what we call the fundamental metallicity relation, which is the relation between mass, metallicity, and star formation rate. So the galaxies that are below the mass metallicity relation, so at fixed stellar mass, if they have lower metallicity, they have higher star formation rate. And the similar relation holds for H1 gas, and that one is even more tighter, so probably more fundamental. And so now the question is, can we understand, for example, this relation with our simple equilibrium model? And it turns out that yes. So for example, imagine that you have your galaxy that is living on your mass metallicity relation, and suddenly you accrete some gas from the external part, from the intergalactic medium. This gas is typically lower it has lower metallicity, so the metallicity of your galaxy will be diluted. So the galaxy will move below the mass metallicity relation. But remember, you accreted some gas, so this gas will be available for star formation. And so naturally it leads to the increased star formation rate. Okay, so this explains why galaxies below the mass-metallicity relation have higher star formation rate. But again, now the star formation is ongoing, stars are formed, metals are formed, so metallicity is again increased. And so galaxy goes back to this fundamental relation, this mass-metallicity star formation rate relation. Similarly, there is some sort of other fundamental relation between the fraction of gas, stellar mass, and star formation rate. Again, it doesn't seem to evolve in this case with the redshift. So there are plenty of these interesting, or these are one of the most interesting and important relations that show that scatter is correlated. Now, so let's go back to this picture that we had here. So, okay, we seem to have addressed and sort of solved the problem at low stellar masses. We seem to need this huge amount of energy to sort of prevent this overcooling problem. We saw that we still don't know the details. We know that the supernova is probably not enough. We need to add all this pre-supernova feedback and probably plenty of other processes that we haven't accounted for. But at least there is a hint that there is a way to sort of improve our understanding. However, there is this knee, and then the relation turns down. So we need, again, some kind of feedback also at high masses. So this equilibrium model suggests that we need some huge amount of preventive feedback. So it could be ejective also, but it cannot be supernova. Why it cannot be supernova? That's because there are these properties we were already talking about, that low mass and high mass galaxies have very different properties. So high mass galaxies are typically quenched, ellipticals with a lot of hot gas, almost no dust, no ongoing star formation. So at high mass, it's not the star formation that will help us because there is no star formation to begin with. Okay? And also, you remember we were talking about the mass of the halos in which the supernova feedback can be efficient, and we derived, or we showed, that this temperature corresponds to the virial mass for halos below 10 to 11 something. So this is not going to be efficient. So the potential well is too deep for the supernova to make an efficient outflows. So what else is there left, right? What can we do? And the community sort of agreed that we should try to extract the energy from these black holes, right? Because these low-mass galaxies tend to have a smaller black holes, relatively speaking, to their stellar mass, and the high-mass galaxies tend to have large black holes. So how to do that? Or is it at all plausible? So it doesn't seem to be that crazy, because there are a few sort of relations that suggest that galaxies co-evolve together with black holes, and you will have lectures on the black holes and all this kind of stuff. So here, take it as a sort of a preliminary view in the context of galaxy formation and evolution. So one hint that it is not a totally crazy idea is that this black hole growth roughly follows the star formation growth. Roughly means qualitatively. There is still a factor of roughly 3,000 to bring this curve to agree with each other. But the point is that it really suggests that there is this coevolution, and that black holes and galaxies accrete or grow by accreting the gas. Another sort of relation that suggests that these black holes and galaxies evolve together is this tight relation between the black hole mass and the stellar mass of galaxies over a large range of masses. And this relation is even tighter when, instead of stellar mass, we consider the velocity dispersion. Okay, so for the elliptical galaxies, velocity dispersion is essentially velocity dispersion of all the stuff, and for the disk galaxies, the velocity dispersion of bulges, right? So the black holes trace sort of the growth of these bulges in galaxies. So again, the main conclusion is that it seems to be suggested from observations that galaxies and black holes grow together, and they are fed by the cold gas. Okay, so how do they grow? So here's the sketch of our basic understanding of what is happening. So we think about black holes as having this accretion disk full of gas and certainly also dust. And in fact, this accretion, so there is a material that will be accreted in this accretion disk around the black holes, but at some point this material will be accelerated and it will generate high energy photons that will push against this infalling gas. And so it turns out, and I think it's the agreement between observations and some detailed models, that only quite a low amount of material, so it's 5 or 10%, will really fall onto the black hole, and all the rest will just find its way and to escape or to leave this accretion disk. And there is a lot of observational suggestion for that. And depending on how this accretion is happening in this accretion disk, you will have a different outcome. And what is important in this is the Eddington ratio, which is the ratio between the accretion onto the black holes and this what we call the Eddington rate. And essentially, every object that has some luminosity has an Eddington rate. So every black hole has some Eddington rate because it depends on the mass of the black hole, right? You have a basic relation for this Eddington rate. So you see it depends on the radiative efficiency and all these details. But the most important thing is that this Eddington ratio, as I said, that is the ratio between the accretion onto black holes and this Eddington rate, will decide what will happen to the gas that is in this accretion disk. So if this Eddington ratio is high, you will end up having these very strong radiation winds that can go up to velocities of few thousand kilometers per second. Whereas at low accretion rate, what you will generate these energetic bipolar outflows that we call jets. And this is because essentially gas, as it is advected, it will advect also magnetic fields, which will be able to align in a perpendicular direction to the disk, and they will able to accelerate this electron at relativistic velocity. So these jets can have very high velocities. And based on that, we talk about two different AGN feedbacks. So this is the way we model that. One is so-called quasar mode, which is typically at high accretion rate. And as I said, it's driving these outflows at velocities of up to a few thousand kilometers per second. And this is something that we can see in observation. So these are seen typically in X-rays or in radio, much less or a little bit in optical, but not that much, and not that much in infrared either. And the second way of model this AGN feedback is through this jet mode that, again, is something that is based on observations, at least qualitatively. And this is activated typically at low Eddington ratios, but it can occur also at high, so the details are very complicated. And the main idea behind is that really these magnetic fields that can create this collimated jet perpendicular to the disk of these galaxies. And again, this is seen very much in X-rays, in radio. You see these nice jets. It's not seen in infrared, neither UV. So why are we introducing this AGN feedback? We need to quench massive stars, right? Massive galaxies. We need to quench the star formation in them, but then we also want to transform them in elliptical galaxies, okay? So how does this work? So we believe that what really quenches the star formation in these galaxies is this jet mode feedback, which in fact blows these bubbles of the hot gas that you can see, for example, in these X-rays that are that we can see also the trace of that is this is the bubbles that are pushed away by these AGN jets with very high velocities, and essentially this will push away this gas, heat this gas, And in terms of how much of the energy or mass can be evacuated, so the jets are very efficient in terms of evacuating really this material and heating this material up to really several hundreds parsec away from kiloparsec from galaxies. So it can have huge importance on the gas that is around the galaxy. And again, there is a lot of observational evidence in terms of these hot bubbles that are seen in X-rays. You see these cavities and the jets that are aligned with them. Okay, does it work? It seems that it sort of works in this cosmological simulation. So here is one example of zoom-in, quite high resolution simulation of the halo in a mass range. So they did a series of this simulation over halos between 10 to 13, 10 to 14 solar masses. And they found that indeed these jets follow qualitatively what we see in observations, and they can really, the net result of this, they can evacuate these halos and then prevent the formation of stars in them. Another way of seeing the effect of these jets is to look at the composition of the gas, so in different phases inside these dark matter halos. And again, you can see it by looking at a numerical simulation and play the game where you include or not some physical ingredients. And you can see what is their effect. So for example, here on the right-hand side, so what you see, you cannot see it, but this is the fraction of the gas that you have inside your, or fraction of baryons that you have inside your dark matter halos as a function of halo mass. So, and different colors are just different phases of the gas plus the stars, so all the baryons all together. So if you have no feedback at all, meaning no stellar feedback, no AGN feedback, you end up having all the baryons inside your dark matter halo because there is no reason that they should leave. Where would they go? But now things start to change when you start to switch on the supernova feedback, so you start to suppress these low mass halos, and then it's even more dramatic when you switch on the AGN jets. You are able to suppress also these more massive halos. So this is another nice way to see this. Okay, so this is much more illustrative or statistical way of seeing that. Again, we are back to the stellar to halo mass ratio as a function of halo mass. And so what we think, how we get to these sufficiently low efficiencies, conversion efficiencies at low mass, we have this star formation feedback that we need to suppress the formation of galaxies. And at high mass end, we need this AGN feedback to suppress the galaxies. And these lines show a few models. So clearly, we need both of them to agree with what is expected or what is measured in observations. Okay, what about the morphology? So here is one nice example of how the AGN feedback could turn spiral galaxies into elliptical galaxies. So this is an example from a numerical experiment where the same simulation was run in two different setups. In one, there was full feedback, AGN feedback, and the second one, everything was the same, just there were no black holes, so no AGN feedback. And so you clearly see, if you can see on these images, so each time on the image on the left is the simulation with the AGN feedback, and on the right without AGN feedback. So clearly we see that without AGN feedback, all these simulations produce these very nice and very massive but very wrong galaxies because they are all spirals or disk dominated. And so the mechanism behind is not direct. It's not like AGN feedback would directly turn galaxy into elliptical galaxy, but it's continuous in the sense that as the AGN feedback is active, it will heat the gas, and typically you have this triggering of AGN feedback after the merger. So imagine two galaxies, they merge, but after the merger, normally they form the bulge, they start to form the bulge, but they could reaccrete a new fresh gas and rebuild the disk. However, the AGN feedback will prevent this. It will heat up and expel this gas, and so it will sort of lock the morphology of this post-merger system, right, or this post-merger morphology. And then more and more these mergers will happen. Galaxy will slowly turn into an ellipsoidal one. Okay, so now let me show briefly some of the comparison of how well we do in this cosmological hydrodynamical simulations compared to observations. So here is just one example, just showing the stellar mass function as different redshift. So this shaded area is observations, and in colors you have 4 different state-of-the-art, as of today, cosmological simulations. So you can conclude as you wish. In my opinion, the conclusion is that we are still not completely there yet, because either we reproduce stellar mass functions at low redshift, but here many of these models were calibrated to do so. So in many cases, it's not a prediction. It's a prediction for this red one, the horizon AGN. But when you go back to higher redshift, you see that you start to have discrepancies for all the models. It's probably, okay, let me skip this. It's probably even more dramatic when we look at this famous main sequence. So the star formation rate is a function of stellar mass. So at low redshift, all these simulations seem to work pretty well. But the discrepancies start to appear at higher and higher redshift, so they seem to have lower star formation rate compared to the observation, so maybe they suppress too much of their stars. And this is even more nicely seen in this SFR function. So this is simply you count how many galaxies you have at the different values of the star formation rate. And so the point here is that, for example, at higher redshift, at the redshift, so high here is redshift 2, there is only one from these simulations that is able to reach such a high star formation rate as those seen in the observation. This is the SIMBA simulation. All others fall well below. But then, on the other hand, when you go to lower redshift, the remaining simulation seems to do better. So this, I think, nicely demonstrates where the field is at this moment. I would say that we are still not there yet. Here are a few other examples where, for example, mass-metallicity relations seem to be nicely reproduced, and also the cold gas fraction. But you probably will have access to all these slides, so you can go through them if you are interested. Okay, I will skip this. Maybe I will show you just quickly. So the way to think about galaxies is that it contain dark matter with gas stars where they form gas cools, they form stars, eject stellar feedback, they form and grow black holes, and so on and so forth. But the important thing is to keep in mind that galaxies are not closed, isolated systems, okay? There are all these inflows and outflows. Galaxies interact and merge. And just for fun, okay, these are a few examples of how I was talking a lot about the cosmological simulations, but what are they? We could have another full lecture on that. So this is just to show you there are different types based on either the volume that they simulate or the physics that are on ingredients that are put inside, because you cannot, ideally we would like to have as large box as possible with all the physical ingredients, but this is computationally very costly, so we need to make some compromises, okay? And this is really just for fun, to show you the complexity of the galaxy formation and evolution. You need to capture cosmological framework, and here are just a list of a few astrophysical processes and the possible ways of how they impact the galaxy. So if you are interested, you can go through that. So I will stop here and I will move to another lecture very quickly, because we have less than 1 hour for 2 lectures that remain. And there are a few things that I would really want to cover. And then
Mm-hmm. But so why in the simulation we underestimate the fraction of point galaxies within that race, because we are not really physically resolving that?
So that's another. So this is one very good point. In all those, so all the plots that I was showing and comparing with the observational results, these were the cosmological simulations. In that part of the plot where I was showing the simulation, which are large boxes, meaning 100 megaparsec cube, but the price to pay is that the resolution is limited, meaning that the best resolution is roughly 1 kiloparsec. So in this simulation, clearly you are not resolving even the disk, right? Think about the disk of the Milky Way, which is like hundreds of parsec, you even don't resolve that. So because of that, you need to use some really phenomenological, what we call the subgrid recipes. We know that we are not resolving the detailed physics, so we try to model it somehow. And there are plenty of parameters, so people usually calibrate it at, for example, redshift 0 observations. You know, imagine star formation prescription. There are few free parameters like the efficiency or something like that. People calibrate that on redshift 0, and they say, okay, this is at redshift 0, it's not a prediction, but I can still go back in time and see how well I do. And this is a sort of infinite process in the sense that if we don't have enough resolution and we don't have enough detailed understanding of the process that we try to model, well, the outcome is what it is. And you cannot rerun this type of simulation. As I said, they are very computationally costly. Sometimes it takes 1 year to fully evolve it down to redshift 0. So this is the best that people, the individual groups of people using different models came out to. So yeah, and again, this will show up differently. So in one plot in this stellar mass, in this main sequence, you are right. They seem to be all below the star formation rate in this plane at redshift 2, but they are sort of doing okay at redshift 0, and I don't think that anyone knows exactly why this is the case. So this is an open question and classical problem in this field.
We can move on
and then have more,
more time for questions.
Okay, so we already saw this picture. We saw that on large scales there is some structure. We understand sort of where does it come from this initial perturbation generated in the primordial universe. And we have this very nice filamentary network seen in the numerical simulations. And essentially, this resembles what we saw on the pictures of the distribution of galaxies on large scales. So in fact, just to give you a little bit of the perspective on that, this type of distribution of matter was for the first time observed in something like 1990s. This was the famous the map of the first CFA redshift slice that really provided the first observational evidence for existence of what we call today the cosmic web. Then, of course, with all the large galaxy redshift surveys, this picture was greatly improved, and they clearly established that, yes, indeed, galaxies are not randomly distributed in the universe. They are organized in this, what we call the cosmic web, so composed of these largely overdense node regions at the intersection of these lower density elongated filaments with underdense void regions in between, surrounded by the two-dimensional sort of wall regions. Now, indeed, so this was the first sort of observational evidence in 1990s, but in fact the first evidence for the existence of something like anisotropic structures on large scales comes from theory. And it was in 1970s where we can say that it was this existence of these anisotropic structures was predicted by Zeldovich. And it was well before, so it's nice to realize that. So it was in 1970s, it was almost 10 years before any observations of these anisotropic superclusters have been made. So it was a sort of a very, very nice step towards the understanding of the structures. So what is that? So it's called the so-called Zeldovich approximation. So what is that? So Zeldovich approximation was formulated for a collisionless fluid, so it's a good approximation for dark matter. And it's sort of, it has a kind of simple form in the co-moving coordinate, and it relates essentially the initial positions of the fluid at time 0 to the final, or to the position of this fluid element at the time t through this explicit relation. So this dt is simply the linear density growth factor, and then we have this vector field, which is the initial displacement field. And the Zeldovich approximation, or the Zeldovich assumed that this initial displacement field is related to the displacement potential, which is directly related to the gravitational potential. So if we consider the conservation of mass, you can write this equation. You just inject this map inside, and here what you get is the Jacobian determinant of exactly this mapping between the initial condition and the position at the time t. And these you can write it very conveniently in terms of eigenvalues of this deformation tensor. Okay, so just focus on this expression for the density at some final time t, because there are a few sort of key features that we can learn from that. So the Zeldovich approximation, strictly speaking, is valid only in the regime where this dt lambda I is much smaller than 1. However, Zeldovich made a sort of prediction that it should be still okay, a qualitatively good approximation at the beginning of nonlinear regime where this dt lambda I is close to 1, and even shortly after that. So what are these two key things that we can learn? So the first one is that the density becomes infinite when this dt lambda I equals 1. And this is also the condition for the formation of caustics. So caustics are the set of surfaces where the density is formally infinite. So imagine at the beginning all these fluid elements are just moving along the straight lines. And they would continue to move on the straight lines if there were no perturbation. But we have some perturbation generated in the initial universe, which deflects sort of these trajectories, and they start to cross. And there is this very nice analogy with the caustics that form at the bottom of the swimming pool. So you can think about the ray lights that are coming from the sun, so from far away, so in parallel direction. But then they hit the surface of the water, which is moving, is not still, right? So there will be the refraction of this ray light, and what you will generate at the bottom are these nice caustics. The second thing is that collapse must be anisotropic. Why? Because the condition where the lambda 1, 2, and 3 are equal is essentially never satisfied for some generic function of the potential. So what does that mean? That this non-spherical, because the overdensities are not spherical, so this non-spherical overdensity will first collapse along one direction, so it will form sort of two-dimensional sheets or pancakes. Then it will collapse in the next shortest direction to form the filament, and finally, along the third one, forming this dark matter halo. So here is just to show you one of the first simulations using the Zeldovich approximation is shown here. So these are the mass particles as they evolved following just the Zeldovich approximation from the initial conditions. And here is a slightly more modern version of that. I just wanted to acknowledge Sergei, who passed away really recently. So it's sort of nice that he was behind all these theories and the simulations that were made very early on. Okay, so where do we stand? So far I was explaining that on one side structures form hierarchically from small objects through mergers to forming dark matter halos, which are these overdensities in the initial density field. And now I talked about, okay, first structures to form are these pancakes, then filaments, and then finally halos. So how does this fit all together? So in 1996, Bond, Kaufman, and Pogosyan came with the picture that was sort of can be seen as the unifying picture of how we understand the cosmic web today. So in this cosmic web picture, essentially, it is the clusters that are at smaller separation, that the mean separation of the clusters that will create this these bridges of high correlation that will evolve then dynamically to form this vast network of the filaments. And so, in fact, in this picture, the order in which the structures emerge is reversed compared to this pancake picture, because the first structures to form are the clusters, then the filaments, and then walls potentially containing all the remaining mass in between all the voids. So this is nicely seen in this n-body simulation, where imagine that you are decreasing your density threshold. So what you will start to see is that first things to appear are these clusters that start to connect with these bridges, and then you decrease the threshold more and more, and you end up having this very nice filamentary network, which is also the structure that I really picks very easily. It is also seen in this Zeldovich map, which corresponds to the initial condition from the n-body simulation. Clearly, it seems that, I mean, the isocontours of the densities resemble much more filaments, so it seems that the sheets are not the dominant structures in this picture. And I also showed in this nice work that, in fact, the correlation, these correlation bridges weaken as the clusters are further and further away, and also as the shear becomes more and more misaligned. Okay, so really summary of how we understand the cosmic web today. So we have this nice, well, you don't see anything, but you remember there are, believe me, there are galaxies that in our universe that nicely follow this cosmic web structure. We understand that this comes through essentially just the gravity that makes this initial fluctuation generated in the early universe evolve in this expanding universe. And this was nicely confirmed by all the types of numerical simulation with larger volumes, higher complexity. And essentially, we can say that cosmic web is essentially the result of the tendency of matter concentrations to collapse and evolve into these elongated structures, and they are already contained in the initial conditions of our universe. So on large scales where the gravity should be the dominant force, its net cumulative impact is really encoded in this tides. And this can be decomposed in two parts. So the one part is this traceless part, which is directly of the Hessian, which is the matrix of the second derivatives of the field. So, and this is directly the definition of the tidal tensor, and this is the part that will imply or will cause the rotation or induce the rotation and distortion of this all-forming objects such as halos and galaxies. And then there is this second part, which is the scalar part or the trace, which is directly proportional to the density through this Poisson equation. And it is essentially this part that has been quite extensively studied in the context of one type of environment, which is typically massive galaxy clusters. And you probably know there are plenty of known relations now that have been derived, like, for example, the morphology density or color density relation, saying that in these massive clusters, galaxies tend to be redder, they tend to have more ellipsoidal morphologies. Okay, so now the thing is that we studied a lot this particular type of environment, so the galaxy clusters. However, what about the rest of the cosmic web, right? The filaments and walls. So this started to be studied only a few years ago in observation. Why? Well, because you need high quality data, you need a lot of data, you need to scan a lot of volume, and so on and so forth. But another thing is also that only relatively recently we got access to tools that allow us to extract from these either simulations or observations individual cosmic web features. So there is a really nice mathematical background that connects this cosmic web morphology to a real mathematical theory that is called the Morse theory. And the main idea is that all these important or very significant features that we find in the cosmic web have their direct and mathematically well-defined counterpart in this Morse theory. So the problem is that the Morse theory, so for example, okay, let me step back because I removed some of the slides, but you have a theoretical background of that in the appendix, so I moved it there. Let me just tell you one thing. Maybe you won't understand everything, but that doesn't really matter, okay? So this Morse theory relies on the definition of what we call ascending or descending K-manifolds. So think about you have the entire space, and the space can be partitions in some dimensional domains. just based on the flow of the gradient, okay, of the underlying field. So, for example, the density field. And these domains will intersect. This will create a sort of branches, so this network. And at the vertices, you will have a critical point. So you probably all know what the critical points are. These are the points where the gradient of the field vanishes. Okay? So it really, all this idea of this nice mathematical background is based on computing the critical points, the gradient, and the flows of gradients. The thing is that the Morse theory applies to well-behaved and nicely defined functions, so typically continuous, twice differentiable, so nothing like our real data, okay? I would think about the galaxy catalog, so these are discrete, there is a lot of noise, and so on and so forth. So, and that's where the recent development in computational topology and geometry comes into play, thanks to development of like a discrete Morse theory plus the persistent homology, that taken together led to development of a tool or the algorithm called disperse, which stands for discrete persistent structure extractor, which is based on this very nice mathematical background that allow us to coherently, without any free parameters, identify all the 4 components of the cosmic web. So I think I will skip this. I already said that, so just one sort of illustration in 2D. So here's a two density field in the 2 dimensions. You have in red the maxima, in blue the minima, and in green the saddle points. And what you see, these arrows, is the direction of the gradient, the flow of the gradient. And in fact, these integral lines follow; they are tangent to the gradient at every point. So this is somehow a very simplified version, basis behind all that mathematical framework. Okay, so what do we do in real life? So we saw that we have nice data on large scale. So, however, extraction of the cosmic web features from observation is still very challenging, because what you need typically is really high sampling, so you need to have access to really high density tracers, and you need a high quality redshift, okay? Because you need to, if you want to do this analysis in 3D, you need to be able to convert the distances with high precision to their positions, to redshifts to the distances, and then to the 3-dimensional positions. So I will just very quickly say that today, we are able to reconstruct the cosmic web in the data up to, let's say, redshift of about 0.8, thanks to spectroscopic and photometric surveys. But at higher redshift, we can use the tomography of the Lyman alpha to reconstruct the underlying density field. However, in between, so in this range between the redshift 1 and 2, there is nothing for the moment. And so this window is very important because, by the way, this is very close to the peak of the cosmic star formation rate density. So it's important for understanding how this large-scale structure impact on the properties of galaxies at the peak of the star formation rate density. And this will be, so the good news, that this will be covered very soon thanks to ongoing Euclid survey, future moons, and PFS. So this is really great. I have now 2 parts where I wanted to give you really some sort of, just so that you know how we do, how we extract the cosmic web from galaxy surveys, and how we do that using the Lyman alpha forest. But I have 30 minutes. And here still, so that would be the rest of this talk. And then I have the 4th one, where I wanted to show you a little bit more of how this cosmic web impacts the properties of galaxies. So what I proposed, that I skip this technical stuff, but again, feel free if you are interested to come and see me, and I can tell you more about it. And I will switch to, for the remaining 30 minutes, for the last part of my talk, where I would like to show you the direct impact of these large scales on halos and on galaxies. Is it fine? Okay. Okay, so let's start again where we were at some point when we were summarizing how we understand today the cosmic web. And so the big question is that okay, we understand that this cosmic web naturally defines the environment in which galaxies form and evolve. But the question that we can ask now is whether it has an impact on galaxy and halo properties. And so let's start with the halo properties. So one of the probably easiest ways to assess this is to look at the assembly history of dark matter halos. And it turns out that depending on where the dark matter halo is sitting within the cosmic web, its growth will be impacted, and this even at the fixed halo mass. So for example, a halo that is sitting at the node of the cosmic web, so it's the region where the cosmic web filaments are connecting. Here's an example from N-body simulation. You see that the material is inflowing onto the halo, and this halo will be able to accrete this gas, right, continuously. And so this will be sort of late type forming halos. When you take the halo of the same mass, but that happens to be embedded into this large and thick filament, which is larger than the size of the halo itself, the halo will see all the material receding away from that, because the material is attracted somewhere here is somewhere the massive nodes of the cosmic web, so all the material will be flowing in that direction. And so the only possible accretion is in this transverse direction, which is really tiny. So this halo will happen to be stalled, right? So it's early forming halo because it stopped accreting very early on. Okay, so this is a sort of, we observe the simulation, we see what is happening. Can we describe it on more theoretical ground? So this was done when considering the conditional excursion set theory by Musa et al., but there are other attempts as well, where essentially this excursion is subject to the presence of the large-scale cosmic filament. So very quickly, in a nutshell, the main idea of this excursion set theory is to compute the statistical properties of some stochastic variable, so let's say our density field, enclosed in some sphere of radius r. So this radius of this sphere can be related to the mass of the final objects through the spherical collapse model we saw on the previous lecture, and is also sort of tracer or the proxy of the evolution, because larger the radius, larger the mass, later the formation time. And now within this context, all these expected values for this stochastic variable can be recomputed subject to large-scale tides that are induced or created by this large-scale structure, which is well described by this filament type saddle point. Why? Because it captures this local geometry of this filament. So here is an example of the result of the isocontours of the accretion rate on the dark matter halo in this framework. So the saddle point is sitting here in this 0, 0 point. So this is the direction of the filament, somewhere here on both sides. So it's perfectly symmetric. So somewhere here is a void, right? So underdense regions and region, and this is a node. So we clearly see one very important outcome of this prediction, which is that these properties, like for example accretion rate, depend not only on the radial distance from the saddle point, so it's not spherically symmetric, but depends also on the angular separation, so the angle between the position and the filament. You can repeat this for other different properties, so this is slightly different representation compared to the previous plot. This is essentially just one quadrant. But the point here is that you can see different isocontours for example, density, mass, accretion rate, but you can do it also for formation time. And there are two main takeaway messages. So the first one is the one that we already said, which is that all of these isocontours depend not only on the radial distance from the saddle point, but also on the orientation with respect to the filament. And the second one is that they are not identical. Okay, so this means that these large-scale tides will impact the different halo properties differently. Okay. Another interesting impact of the cosmic web on the halos and galaxies potentially is on the side of the angular momentum. So in the theory that revisited this linear tidal torque theory that we saw during the first lecture, show that if you put the forming objects in the vicinity of this anisotropic cosmic web, so nodes, filaments, walls, and voids, this will induce the preferred directions for both the inertia tensor and the tidal tensor. Remember, in the linear or the linear level, so tidal torque theory tells you that the angular momentum is proportional to the misalignment between the inertia tensor and the tidal tensor from the surrounding material. And here, the presence of the large-scale structure will induce this preferred direction, which will turn out eventually to be a preferred direction of the angular momentum. And this is a nice summary of this prediction, which shows, so the saddle point is here. This is the plane of the saddle. The red thing is the filament embedded in a wall. And these arrows show the angular momentum of dark matter halos. And so you clearly see in this mean spin field representation, in this geometry, we see that the halos that form in the plane of the saddle tend to have the angular momentum aligned with the neighboring filaments, whereas if they move, as they move towards the node, they tend to have their angular momentum in a perpendicular direction. And this depends on the mass. Again, the theory is able to predict that, and it's in agreement with the measurement in numerical simulations. And essentially, the thing to remember is that, and the consequence of all this is that low mass halos are expected to have their angular momentum aligned with the filament, whereas the high mass halos tend to have their angular momentum sort of perpendicular to the direction of the filament. And the last sort of impact, possible impact of the large-scale structure of the cosmic web on the halo properties is through this cosmic connectivity, which is simply the number of filaments that are connected to a node of the cosmic web, and in this context, so potentially to the halo that is sitting at the node. We saw that these filaments are defined a preferred direction through which or from which the material will be funneled down to halos and the galaxies. So it's not surprising that the cosmic web is a sort of natural probe of the growth of the structure. And today we really think that it's one of the key ingredients that is driving the assembly history of halos and galaxies. So again, there is a full theoretical background that is able to predict also from Gaussian random field, for the Gaussian random fields, what the connectivity should be. So here are shown some measurements made in this very large n-body simulation, showing essentially, so the main point is that this connectivity is correlated strongly with the mass of the halo. So the more massive halos have higher connectivity, meaning that these massive halos tend to be connected to more filaments. And this is perfectly in agreement with the prediction for Gaussian random field, where also the connectivity is seen to depend on the height of the peak in the underlying density field. So this is something that is expected. Okay, so now what about galaxies? So I will show you in the 15 sort of remaining minutes the impact of the cosmic web on galaxies and what we have learned recently thanks to large galaxy redshift surveys and how this compares with the high dynamical simulations. So there are a few facts that we learned about the impact of the cosmic web on galaxy properties. The first one is what we call the mass segregation. That is, that more massive galaxies tend to be located closer to the filaments of the cosmic web compared to their lower mass counterparts. And this has been consistently measured in all these surveys up to a redshift of about 0.9. Similarly, there is a so-called SSFR, or the color segregation, which says that passive or red galaxies, so passive galaxies are those that are quenched, right, at a very low specific star formation rate, that are closer to the filaments, but at fixed mass. Okay, so now we go beyond the effect of the stellar mass. So at fixed stellar mass, passive galaxies tend to be located closer to the filaments compared to the star-forming or the blue galaxies. And again, this has been found in the observations up to redshift of about 0.9. Similar segregation was found also with respect to the walls. And this is broadly consistent with the measurement through a series of state-of-the-art cosmological simulations that we were discussing previously. So qualitatively, it's in a good agreement. Now, another type, of course, of segregation, you can think about all possible properties of galaxies you can measure. So here's an example showing that a central galaxy, so this time we're focusing only on the centrals, at fixed stellar and halo mass that are closer to the nodes, filaments, and walls, tend to be more metal-rich. They tend to be older and have higher enhancement by the alpha element. So this is a result only from a very local universe thanks to SDSS. And similarly, there has been a measurement of the gas phase metallicity. Again, galaxies at fixed stellar mass and also the local density, galaxies that are located closer to the filaments of the cosmic web tend to have, and the nodes as well, and it's more prominent in the nodes, tend to have higher gas phase metallicity. This can be also seen in the impact of the fraction, what we call the fraction of red galaxies, which is simply the fraction of galaxies that are quenched or that they have a low specific star formation rate compared to the total amount of galaxies. We see that as we get closer to the filaments, the red fraction increases in different distances from the node. Okay, so we can see this double impact on this property. Again, this is consistent, at least with some numerical, high dynamical cosmological simulations, and these results have been done only in the local universe. So there is still a lot of work to be done with the future surveys to extend all these measurements up to higher redshift and even beyond the redshift 1, which will be possible in the near future. Okay, what about the angular momentum? So let me start by showing the measurement from high dynamical simulation. We confirm the theoretical prediction and expectation for the dark matter halos. For galaxies, the same effect is true. As a function of stellar mass, we have a different tendencies for the orientation. So the massive galaxies tend to have their spin perpendicular to the galaxy, to the nearby filaments, whereas the low mass galaxies tend to be aligned with the direction of the filament. And again, this is consistent qualitatively across very different cosmological simulations, and very different, I mean, in terms of implementation, but also the codes, which is important. What about observations? So there has been, so it's more tricky because it's very hard to measure the angular momentum of observed galaxies in 3D. We typically can do that only for galaxies that have some disk component, right? And so this has been done for spiral galaxies, and indeed it was confirmed in the low redshift universe that these spiral galaxies tend to have their spin aligned with the filament. And for S0, so S0 galaxies are galaxies that have very prominent central bulge, so they are sort of like ellipticals or something like that, but still have some disk and disk component, and those seem to show a really preference for the perpendicular orientation. And also it was shown at low redshifts using this SAMI sample that this transition mass is driven essentially by the mass of the bulge of the galaxies. Similarly with walls, I will skip this. This is, okay, so now what about the interpretation? Okay, I was just listing the observed trends, and I was showing before some predictions from theory and measurements for halos. So we can sort of summarize all the possible interpretation. There are what physical processes are at play. So I was arguing that it's the assembly history of halos that impacts on the mass, on the density, on the accretion rate, and so on and so forth. But this was, strictly speaking, applicable. We could have applied it only on dark matter halos. So what about galaxies, right? So we can do this measurement in high dynamical simulation. So I'm showing just here a setup. Again, here this point is the filament type settle point. So this is sort of direction of the filament, and here direction towards the voids. And you have it in the 3 dimensions. So you can stack all the galaxies in your simulation, and then cut these planes, so the longitudinal and transverse plane with respect to this settle point, and make the same isocontours as derived in the theory. So here is one example of these isocontours. So again, the settle point is here. This is the direction of the filament. These are the nodes, okay? And these are the 2 voids. And so we clearly see, so the colors are the isocontours of the stellar mass. So again, first important things to note is that these isocontours, they depend not only on the radial distance from the settle point, but also on the orientation, right? And the second thing, we can clearly see that in terms of the stellar mass, we find or we reproduce what we have seen. As galaxies are getting closer to the filaments, they are more massive. and along the filaments, galaxies are more massive near the nodes. So you can play this game and compute it for all different properties. So here is, for example, the age of galaxies. And we realized that there are a few properties that qualitatively follow the trends of the stellar mass, like is, for example, visible here for the age. So you can say, okay, so it's the stellar mass that is driving sort of this property. However, there are a few of them that are very different. And this is the case for morphology, as shown here in terms of V over sigma, which is the ratio of the rotation over dispersion dominated velocity of stars. But it's the same thing for the specific star formation rate. So clearly we see just from the naive comparison that the stellar mass is not enough to explain these isocontours. So what could that be? Well, you can play a game and say it could be the local density, and on top of that it could be the halo mass. And if you put all these together, you can compute the residual. So what is left once you accounted for all these three components, that is stellar mass, halo mass, and the local density. And for the age, we see that there is almost nothing left. Okay, the residuals are very close to zero, so we can claim that we sort of explained by all these three parameters this quantity. However, for morphology, I don't know if you can see it, but not only the residuals are very high, but also they have this typical geometry that shows up in this reference frame of 7. So what is causing this? And we are going back to this acquisition of the spin. So here I'm showing, this is similar thing that we saw on that nice figure showing the geometry of the spin of the halos. Here is just cut, like you cut the slices, and you see that you have this quadrupolar structure of the spin, but it's also true for the vorticity, so this rotation of the gas inside the filaments and near the walls. And so the conclusion is that it's the advection really of the angular momentum that has a strong impact on these properties of galaxies, such as specific star formation activity or morphology of galaxies. Okay, so this was this interpretation. There are other possible interpretations or the processes that we know that play a game. They are important, so let me just highlight this one because it's sort of interesting, which is when you look at the halos that contain some gas, it turns out that depending on where they come from inside the cosmic web, they can be impacted by the processes such as round pressure stripping. So these are a few examples of these halos. You see this typical characteristic jellyfish-like morphology, that is tracer of this presence of this round pressure stripping. And these are the halos that just crossed the wall. So what is happening there? So these halos, they go with the flow. They are expelled from one void, and they approach the wall. So as they approach the wall, they move with the global flow of the matter. So they can continue to accrete their gas because their relative velocities are pretty low. But once they cross the wall, now they happen to be moving against the gas that is coming from another wall from the other side. Okay? So suddenly their relative velocities will be very high, and they won't be able to accrete a lot of gas. And at the same time, they will suffer from this round pressure stripping. So this could be another interpretation of shutting down the star formation in this large-scale environment. And this one I will skip. Let me say a few words again about this cosmic connectivity, which I find very interesting. So if you can see it, so here I am showing the distribution of gas from the hydrodynamical simulation on large scales. You can clearly see even by eye these gaseous filaments that drive the material down to halos. Then on top of that, if you can see, there are dots that appear. These are the galaxies, and from that we can reconstruct the cosmic web, which can inform us, or we can deduce the connectivity, which again I recall is a number of filaments that are connected to these nodes, and we can ask the question. We saw that it's correlated with the halo mass, but can we say something about galaxies? So we can go to the local universe, so SDSS, and compare with numerical simulation. So here is shown just the probability distribution function of this galaxy connectivity in the data, so the real universe, and two different simulations just for comparison. So we see that the agreement is pretty nice. The mean value is 3. So on average, galaxies seem to be connected to 3 filaments. This, of course, galactic connectivity as well is a function of stellar mass. So more massive galaxies tend to have a higher number of filaments connected to them. We can also see the impact on the star formation rate and also the morphology. So, for example, at fixed stellar mass, galaxies that are passive or that are typically dominated by some ellipsoidal component tend to have higher connectivity compared to the star-forming and irregular galaxies. And this is also seen when we look at the residuals, when we account for the underlying mass dependence. So this is important because we always need to distinguish, is this galaxy property driven primarily by the underlying intrinsic property, which is the stellar mass, which indeed drives many of their properties. But here we see that once we account for this dependence, and this is shown in the terms of these residuals, we still see this difference in terms of connectivity for passive and star-forming galaxies, where passive galaxies have higher connectivity. And the same thing for the morphology. And here is just quickly to show you qualitative agreement with high dynamical cosmological simulations, both for the calculation of the connectivity as a function of stellar mass and also in terms of these residuals. Okay, another interesting thing in the simulation, we can look at what about the halo mass. So here what I'm showing are this time the results from the numerical simulation. So the connectivity is a function of halo mass for galaxies at redshift 0, split according to 3 different properties in the lowest and highest quartile. So on the left, stellar mass, in the middle, specific star formation rate, and on the right-hand side is V over sigma, which is a proxy for morphology. So high V over sigma means disky galaxies, low V over sigma means sort of spheroidal galaxies. And so we clearly see that even at fixed halo mass, there is a clear difference of these properties as a function of connectivity. So galaxies that have higher connectivity tend to have higher stellar mass, lower specific star formation rate, and tend to be more ellipsoidal. Okay, so here this is just a sort of a summary picture showing that I hope that you are now convinced that if we really want to understand formation and evolution of galaxies in this, have the full picture of it in this multi-scale baryon cycle, we need to consider really all of these processes across all the scales. And here are a few sort of surveys that started already to be available and will be available later on. One of the exciting one is Mosaic on ELT. But also SKA, and all these will help us to get a much better understanding of how not only galaxies but structure as such formed. So I can leave this. I had another part, but I'm not going into that. You can ask me, which was on, essentially, I will just tell you what was that about, so in case you are interested, you can ask me, whether the small-scale galaxy physics, like the astrophysical thermal and non-thermal processes associated with stellar and AGN feedback can have an impact on the distribution on large scales and therefore on the large scale structure themselves. So this was one topic. And another one was the link between the cosmic web features, the specificity of the cosmic web features and the cosmology. So can we learn something, can we constrain the cosmology using cosmic web and its individual components? And I think I will stop here. So thank you very much.
I take just one comment for the questions is that I suspect that we could have developed this specific topic during the full week.
Exactly.
So
Yeah. Essentially, every of these lectures could have been a 1 week long discussion. Yeah. So sorry if it was quick, but.
Some questions?
May I ask, what is the spatial resolution in your simulation?
So most of the simulations that I was showing in this part of the talk are those that are large-scale cosmological simulations, meaning relatively large boxes of volume of 100 megaparsec cube, but the resolution, the spatial resolution, is quite poor, and it's this famous 1 kiloparsec that I was mentioning before.
Kilo per second?
1 kiloparsec, 1 kiloparsec, which is terrible. I mean, you don't resolve the small scale physics, you don't resolve the regions of star formation, but still, that's what we have in a sort of statistical sample.
As I know, it's the virial radius of a halo. 1 kilo per second is the virial radius of a halo. Yeah, the radius of halo is about 1 kilo per second, right?
No. 1 kiloparsec is the spatial resolution, so it's the smallest scale that you can resolve in the simulation. That's what I mean. So you, spatial resolution.
Sorry.
Yeah.
Spatial resolution could be less than 1 kilo per second in simulation.
It could be, but if you want to run a simulation that has the volume of 100 megaparsec cube and you want to increase the spatial resolution, well, you have to pay the price, which is the computational time, and it becomes really complicated.
So
It's very expensive, yeah.
So when simulate the cosmological wave, how to deal with star formation? Because I think the star formation is in the center.
Very good question. Yes. So this is done by doing what we call the subgrid recipes. So it means that we know why it's a subgrid, because we know that we don't resolve it, but at the same time we know we need to model it because of all the things that I was showing. If we were not modeling the star formation, you have this overcooling and all these problems. So the subgrid recipe means that you simply adapt your prescription of how you form stars in this simulation, for example, if we talk about star formation, and you adapt it to the resolution that you have. Okay? Mm-hmm.
Other questions or comments? Well, if not,